In exercise 232, they're asking you to draw resonance structures for a few compounds. And in these compounds, you'll notice that there will be more than one, more than one of the 5 resonance patterns. So we'll be combining them. First step is to draw in the lone pairs. None of the carbons have a lone pair because none of them have a negative charge. And this oxygen has 2 lone pairs in order to get 8 valence electrons. It already has 2, 4 in the bonds, so it just needs 4 more. Okay, so we'll go through one by one each of these 5 patterns for this molecule. So first, is there an allylic lone pair? Well, that's our first pattern. We do have a lone pair, but it's not one atom away from an atom in a double bond. It's on an atom in a double bond. So although it's a lone pair, it's not allylic. So we don't have that pattern in this structure. How about an allylic positive charge? Well, we also don't have any positive charges in this molecule, so we don't have that one. How about a lone pair adjacent to a positive charge? Well, there's no positive charge in the molecule as drawn, so we don't have that one. How about a pi bond between 2 atoms with different electronegativity? There are 2 pi bonds in the molecule. Remember, a pi bond is every bond after the first bond. So we've got double bonds in these 2 places. This one on the right, that pi bond is between 2 carbons. So the 2 carbons have the same electronegativity, so the pattern isn't there. But for the double bond on the left, that bond is between a carbon and an oxygen. And oxygen is really electronegative. So that would be an example of that 4th pattern. So we have that. So we know we have resonance, and so we can draw in those big brackets that tell people, watch out, anything we draw here, anything we draw is not going to, any structure we draw won't be the molecule itself. The real molecule, the resonance hybrid, will be the average of all of these structures that we draw. So we'll draw that molecule in, and just so that we have them, I'm going to draw in the hydrogens. So all of the carbons in the molecule, or I should say none of the carbons in the molecule has a charge, so all of the carbons in the molecule need 4 bonds. And so you can count them up and you'll see that you get 4 bonds to each of these carbons if you add this many hydrogens. And I'm just going to go fast through that and draw them in because we've done a lot of practice on that in previous videos, and this question will be long enough even just going quickly through that. So I'll assume we're at the point now where you can see the hydrogens that are there. Okay, the curved arrow pattern for having a pi bond between 2 atoms of different electronegativity is that the pi electrons go on to the more electronegative atom. So we'll draw that special arrow, resonance arrow, that tells you to take the average, and then you copy the molecule. And anywhere where you have the tail of a curved arrow, that's a place where electrons are moving away from, so erase those electrons. Anywhere where you have the head of a curved arrow, that's a place where electrons are arriving, so you draw electrons in. If the head of a curved arrow is pointing at an atom, like it is here, then you draw the electrons as a lone pair. So we'll draw a lone pair there. And so hopefully also another thing that I'm going to assume you can know by this point, we've done a bunch of practice with it, is calculating the formal charges. So you might see, hopefully you can see here that this oxygen has a -1 formal charge and the carbon has a +1 formal charge. The oxygen is 6 minus 6 dots in 1 line, so that's -1, and the carbon is 4 minus 0 dots in 3 lines. It's +1. Okay, so now we've gone through that structure, and what you want to do is you want to make sure for every single structure you go through all 5 patterns. So we still haven't gone through all 5 patterns for this first structure. we still have to consider this last one. Are there conjugated pi bonds in a ring, alternating single and double bonds all the way around a ring? And there's not. We don't have a ring, so we don't have that one. So we've looked at all of the possible resonance structures for that first structure, all the possible resonance patterns for that first structure. All right, now let's consider this second structure. We're going to do the same thing. One by one, go through each of the resonance patterns. See if we have it. So the first one, is there an allylic lone pair there? Well, we have lone pairs on this oxygen, but they're not one atom away from an atom in a double bond. If you go one atom over, you have this positive charge here. So we don't have an allylic lone pair. How about an allylic positive charge? That's the second pattern. And we do. This positive charge that's here is one atom away from an atom in a double bond. If you go one atom over, you're at an atom in a double bond. So that is an allylic positive charge. And we'll want to draw a new resonance structure for that. So you would take the molecule and copy it. When you have an allylic positive charge, the curved arrow pattern that goes with that is that the pi electrons go to form a new bond toward the positive charge. And so anywhere where you have let me draw that in here. So anywhere where there's a tail of a curved arrow, that's a place where electrons are moving away from. You erase those. And anywhere where you have the head of a curved arrow, that's a place where electrons are arriving. And so you want to draw electrons in. If the head of the curved arrow points at a bond, then you draw the electrons that are arriving in as a bond. And so now, if you go back and you calculate the different formal charges, you'll see this carbon is now 0 because it has 4 lines around it, and this carbon over here is now positive 1 because it has only 3 lines around it. Okay, we're still on this second pattern. We want to go through all 5 patterns with that one. So the next one to consider is the third one. Is there a lone pair next to a positive charge? And there is. Okay, we've done this curved arrow already. There is a lone pair next to a positive charge. These lone pairs next to that positive charge. In that pattern, the lone pair goes to form a pi bond toward the positive charge. Notice that if you do that, you end up getting the same structure as this one on the left. So we've already drawn the resonance structure that you would get from that. It's a pattern we have, but we've already drawn the result. So you don't have to draw the same molecule twice. All right, next. How about a pi bond between 2 atoms of different electronegativity? We don't have that one here because we have a pi bond, but it's between 2 carbons, and so the carbons have the same electronegativity, so we don't have that pattern. And last but not least, do we have a conjugated pi bonds in a ring, alternating single and double bonds all the way around a ring? We don't even have a ring, so we couldn't have that, so we don't have that there. Okay, so we've drawn all the resonance structures we possibly could from those first 2 molecules, or the first 2 structures. So let's go to this third one and go through the 5 patterns with that. Is there an allylic lone pair? There is. All these lone pairs on that oxygen are 1 atom away from an atom in a double bond. You go 1 atom over and you get to an atom in a double bond. So you could have that pattern, and I'll just draw another resonance arrow. You can copy the molecule. And so the pattern of the curved arrow pattern that goes with that is that the allylic lone pair goes to form a pi bond toward the double bond, and the double bond goes to form a lone pair on the atom in the double bond away from the allylic lone pair. Right, so that's what we're going to do here, and anywhere where you have the tail of an arrow, those are electrons that are going to be moving away from there, so you erase those. And anywhere where you have the head of an arrow, that's where electrons are going to be arriving, so you want to draw them in. If the head of the arrow points to a bond, then you draw the incoming electrons as a bond. So we'll draw those as a bond. All right, next curved arrow, anywhere where you have the tail of a curved arrow, those are electrons that are going to be moving, so we'll erase those. And anywhere where you have the head of a curved arrow, that's where electrons are going to be going, so you want to draw them in. If the head of a curved arrow is pointing at an atom, like it is here, then you draw in the lone pair. You draw in the electrons as a lone pair. So you'd have this. Now, if you go through and calculate the formal charges with that, you'll see that this oxygen has 0, and the carbon over here with the lone pair has a -1. So that's a curved arrow we would get from that. So we have this pattern, and we drew the possible resonance structure we get for that. So right now we're still going through the 5 patterns for this structure. And so we go through the next one. Is there an allylic allylic positive charge? There is. This positive charge here is 1 atom away from this atom in the double bond. This one right here. So the thing is, though, if you drew the pattern for that with the pi bond going toward there, you just end up with the previous resonance structure. So you don't have to draw that out. We do have this pattern, but we've already drawn the structure you'd get from it. How about a lone pair next to a positive charge? That we don't have. We have lone pairs, but the atom next to it does not have a positive charge, so we don't have that pattern in that structure. How about a pi bond between atoms of different electronegativity? That's the next one. We don't have that. We do have a pi bond, but it's between 2 carbons, and the carbons have the same electronegativity, so we don't have that. And last but not least, in this third structure, is there a conjugated pi bond? Are there conjugated pi bonds in a ring, alternating single and double pi bonds all the way around a ring? And there's not. We don't have a ring, so we don't have that structure either. Okay, so we've drawn all the possible resonance structures we could for these first 4 structures. So now we'll go through each of the 5 patterns with our next structure down here. All right, first, do we have an allylic lone pair? We do, actually. This lone pair right here is allylic. If you go 1 carbon over, you're at an atom in a double bond. So that's allylic, but if you did the curved arrow pattern for that, and you moved this lone pair here to create a pi bond there, and you pushed the pi electrons in the pi bond onto the more electronegative atom, you'd just end up with the structure you have right above. So we do have that pattern, but we've already drawn it. We've already taken that into account, so we don't have to draw it again. How about an allylic positive charge? That's the next structure here. We have just 1 positive charge. It's over here, and it is not 1 atom away from a double bond. The 1 atom it's away from is not involved in a double bond. So we don't have an allylic positive charge. How about a lone pair adjacent to a positive charge? That we do have. This lone pair, if you go just 1 atom over, you're at a carbon with a positive charge. So we do have this pattern. So when you have that pattern, the lone pair would go to form a pi bond toward the positive charge. But notice the structure that you'd get from that would be the very first structure that you ever drew. So we already took that into account. So that we do have that third resonance pattern, but we've already drawn the structure you'd get from it. And then the fourth one, do we have a pi bond between 2 atoms of differing electronegativity? We do. We have a double bond there between a carbon and oxygen. And oxygen's really electronegative, whereas carbon is just average. So we do have that pattern, and we'll need to draw the resonance structure that gives us. So you can take that structure, copy, and then when you have a pi bond between two atoms with different electronegativity, the pi electrons go onto the more electronegative atom. That's the pattern there. So wherever the tail of the arrow is, those are electrons that are moving away from there, so you erase those. Wherever the head of the curved arrow is, that's where electrons are arriving, and so you'll draw them in. If the head of the arrow is pointing at an atom, then you draw the incoming electrons as a lone pair. And so now if you figure out the formal charges on everything here, you'll see that the oxygen has a negative charge, and the carbon it's bonded to here would have a positive charge. Okay, we're still going through the 5 patterns for this. We just threw the 4th one. We should consider the 5th one. Do we have conjugated pi bonds in a ring? No, this molecule does not even have a ring, so you couldn't have that. Okay, so now you would want to consider this next one. And we'll go through the 5 patterns there. So first, is there an allylic lone pair in this molecule? There's not. We don't have any double bonds or pi in that molecule, so there's no allylic position. So we don't have that. For the same reason, we can't have an allylic positive charge. We just don't have a double bond, so nothing can be one atom away from an atom in a double bond. Do we have a lone pair adjacent to a positive charge? Yeah, we've got a couple of those. We definitely have that. But notice, no matter which lone pair you look at, this top one coming down, that would give us this structure here. Or this middle one going to the left, that would give us this structure here. Or the middle one going to the right, that would give us this structure here. So no matter what type of pattern you try to apply there, we've already drawn the structure for it. And so we've already taken that into account. We don't have to draw anything new. How about the 4th one? Do we have a pi bond between two atoms of different electronegativity? No, we don't even have a pi bond. And the 5th one, do we have conjugated pi bonds in a ring, alternating single and double bonds in a ring, all the way around a ring? No. So we've gone through all 5 patterns for every possible resonance structure, and we see that there are 5 resonance structures here. And that just means that this molecule, the charges in it are really spread out, so it's really stable, and it's going to be really rigid. Bonds that we might have thought were single bonds, we can now see are actually a little bit more than that. They have a little bit of a pi bond, which means that they can't rotate anymore, because those pi bonds would have to break if you tried to rotate, because they come from the overlap of parallel p orbitals, and when the bond would rotate, the p orbitals wouldn't be parallel anymore, so you'd have to break the bond. So those are these structures. Now, that would be the perfectly good solution for this. One thing you might notice is sometimes they may not list all of these structures because not all of the resonance structures are equally important. You take the average of them, but some of them, it's like a weighted average. Some of them are weighted more. The more charges you have in a resonance structure, the less significant it is. So for example, the last structure that we drew is not particularly significant. It's there, it makes a tiny, tiny contribution, but the truth is, so many charges, we have 4 full charges in the molecule, and especially charges where there's an opposite charge, positive and negative charge, on 2 neighboring carbons, atoms that have the same electronegativity, it really lowers the significance of that structure and the weight that it's given when you average them. So sometimes people, like solution, if you look at the solution manual for the textbook that this is coming from, they won't even list that structure in the solutions manual. But for our purposes, you could just draw every structure and leave it at that. Just know that the more charges are in a structure, the less significant it is. So the true structure is never any of these. Never at any point does it look like any of these. It is always just the average of all of them. All right, let's try doing the same sort of thing with B. So here, first step is to draw in any lone pairs. Now we only have carbon here, and none of the carbons have a negative charge, so there are no lone pairs we have to worry about. So we're really just drawing this molecule, and we'll go one by one through each of the 5 resonance patterns and see if we have them. Do we have an allylic lone pair? No, we don't have any lone pairs, so we don't have that one. Do we have an allylic positive charge? We have a positive charge. If you go one atom over, you're at an atom in a double bond, so we do. That is an allylic positive charge. So we have resonance, and so we'll draw those big brackets that warn people. None of these structures is the true structure. The true structure is the average of all of them. We'll draw that molecule. Okay, so just so we can calculate formal charges a little more easily, I'm going to draw the hydrogens in. We've gone through how to do that in detail in previous videos, so I'm just going to draw them in, and hopefully you'll be able to see that they make sense. If not, I encourage you to go back and review the process for figuring that out in other videos. Okay, so those are all the hydrogens there. So we have an allylic positive charge, so when you want to draw the resonance structure for that, you copy that original molecule, and wherever the double bond that the positive charge is allylic to, those electrons go to form a new pi bond toward the positive charge. That's the pattern there. And so whatever electrons are at the tail, those are the electrons that you're moving, so you erase those. Wherever the head of the arrow is pointing, that's where the electrons are arriving, so that's where you'll draw them in. If the head of the arrow is pointing at a bond, like it is here, then you draw the arriving electrons in as a bond. So you'd have this here. And if you go through and calculate the formal charges on all of these things, you'll see that this carbon now has a 0 formal charge, and this other carbon now has a positive charge. Okay, so that's that. We're still on this first structure. We've gone through the first resonance pattern. We saw we didn't have it. We did have the second one, and we drew the resonance structure that comes from that. For the third one, do we have a lone pair adjacent to a positive charge? We don't. We don't have any lone pairs in the molecule. Do we have a pi bond between atoms of differing electronegativity? We don't. We have 2 pi bonds, but both of them are between carbons. So the 2 atoms in each of those double bonds has the same electronegativity. So we don't have to worry about that. How about conjugated pi bonds in a ring? That's alternating single and double bonds all the way around a ring. We don't have that because we don't have even a ring, so can't have that. So we've drawn all the possible resonance structures for that first molecule. Okay. How about now we'll go through each of the 5 patterns for the second one. First, allylic lone pair. No, this molecule does not have a lone pair at all, let alone an allylic one. How about an allylic positive charge? We definitely have that. This positive charge is allylic to 2 double bonds. If you go 1 atom to the left, you're at an atom in a double bond. If you go 1 atom to the right, you're at an atom with a double bond, in a double bond. So that's allylic in 2 places. Now, if you look at the pattern on the left, where the pi electrons go toward the positive charge, that would just bring you back to our original structure. So you don't have to draw that one. But if you look at the pattern on the right, with this pi bond going to form a bond toward the positive charge, that would give us a new molecule, so we do want to draw that structure. So we'll take the molecule we have here, copy it, and then anywhere where there's the tail of a curved arrow, those are electrons that are going to be moving away from there, so you erase those. Anywhere where we have the head of a curved arrow, that's where electrons are arriving, so you draw them in. If electrons ever arrive at a bond, then if the head of the curved arrow is pointing at a bond, then the electrons arrive as a bond. That's how you draw them in. If you calculate the formal charges here, you'll see that this carbon no longer has a positive charge, and the carbon at the far right does have a positive charge. Okay, we're still on this one. We're looking at the 5 resonance patterns. We're going to go through all 5 of them. Does that have a lone pair? Our next one is a lone pair next to a positive charge. No, it doesn't have a lone pair. Does it have a pi bond between atoms of differing electronegativity? No, it has 2 pi bonds, but they're both between carbons. And obviously one carbon would have the same electronegativity as another carbon. And then, does it have a conjugated pi bond in a ring? Conjugated pi bonds in a ring, it doesn't, because we don't even have a ring. So we've gone through all the 5 patterns for that second structure. How about the third one? For that third structure, we don't have an allylic lone pair because there's no lone pair. We do have an allylic positive charge, but notice if we fill in the curved arrow pattern and see how the electrons move, you'd see that it brings you back to a structure you've already drawn. So you don't have to draw a new structure for that. It does have this pattern, but we've already taken care of that structure, the structure that would give us. How about a lone pair adjacent to a positive charge? No, we don't have a lone pair in this molecule. How about a pi bond between atoms of differing electronegativity? Nope, all the pi bonds in this molecule are between carbons. How about conjugated pi bonds in a ring? Nope, we don't have a ring. So for each of these, we've gone through all of the possible 5 patterns for each resonance structure, and so we know that this is going to be the complete list of the resonance structures. So the true structure never looks like any of these. It always only looks like the average of all of them. So if you were to erase those hydrogens so that you get that bond line structure where the hydrogens are just implied, you'll see it'll look a little less complicated or a little less confusing. And those are your 3 structures. You can keep the curved arrows or not. Those are your 3 resonance structures. So this true structure would look something like this. So all of the bonds are something in between single and double bonds, and there is a slight positive charge in 3 places. That's sort of the average of these 3 structures. So notice the charge gets spread out. In our original structure, it looked like just one atom had a full positive charge, and that would be really uncomfortable or very reactive for that molecule. But in the true structure, that charge is spread out, and there are 3 atoms that have a slight positive charge instead of a full one. The charge gets smaller in any place, and so it's more manageable. So that stabilizes the molecule. It makes it more rigid. After all, in this structure, it looks like these are single bonds, and single bonds can rotate, but we see that none of them are single bonds, so none of these bonds can rotate, so the molecule is more rigid, so it's more stable, more rigid. And lastly, we see places where there's charge that we wouldn't have seen in our original structure. And those are going to be places where reactions could happen. If you had a negative charge, you could attack in 3 places. You would have only predicted 1 if you hadn't drawn the resonance structures. So I'm going to continue the rest of the exercises in this problem in a separate video just to avoid making the videos too long.